Hello, Math Study students, and welcome to your online lesson. In this video, we'll be continuing our discussion of geometric sequences by looking at a few more examples. A quick reminder that an arithmetic sequence is a pattern where we're adding a fixed value, known as the common difference, to get the next term. A geometric sequence is one where we're multiplying a fixed value, known as the common ratio, to get the next term. So looking at this example, example 3 here, we are asked to find k given a geometric sequence with the consecutive terms k, 3k, and 12. So we looked at a very similar example to this a couple videos back when we were talking about arithmetic sequences. And we have three numbers in a row. Consecutive means in order. So if I was talking about numbers on a number line, that'd be like 1, 2, 3. I'm not jumping around to something like 7. That would not be consecutive. So next to each other. So this term here, k, could be like the first term in the sequence, or it could be the fifth term, but whatever it is, let's say it is the fifth term, then 3k would have to be the sixth term, the one that comes right after that, and 12 would have to be the seventh term coming right after that. Well, with any terms of an a geometric sequence, similar to the example we had looked at before, 2, if I multiply by a common ratio of 3, I would get 6. And then 18, I can show that these numbers can be set equal to each other if I take pairs of them and divide backwards. So 6 divided by 2 is the common ratio of 3, but so is 18 divided by 6. And I could set those equal to each other because they're all equal to 3, and so therefore they're equal to each other. Well, we're going to do the same idea here, except now we have some k's involved. So we are going to take 3k, the second term, and divide the term in front of it, which was k. And that should be equal to the common ratio. And then I'm going to set that equal to the third term divided by the second term, 3k. And that would also be equal to our common ratio. All right, so now how do we solve this? Well, we have two fractions set equal to each other, and a very common way to do this is to cross multiply. So we can multiply straight across here, straight across there. And so I have 3k times 3k, which gives me 9k squared, because we have a k times a k, giving us k squared. The 3 times the 3 became the other. 12 times k gives us 12k. And technically this is a quadratic, and so we should look at methods for solving our quadratics here. But to make things a little bit simpler, and this is kind of cutting corners a little bit, but I can see there's a k on each side. And so if I divide out a k, those can cancel out, and k squared divided by a k, well, k squared is k times k, and if I'm dividing one of those k's, I would end up with 9k now is equal to 12. And then the last step is I'm going to divide both sides by 9 to get rid of the 9 and have k all alone. So k is equal to 12 over 9, and if I want to reduce that, k is equal to 4/3. So we found k. Now I want to check to make sure it is correct. And so that would mean that my first term was 4/3, k. And then my next term is 3 times 4/3. And then my last term is 12. All right, so now let's simplify our second term. We have a 3 multiplying. We also have a 3 dividing, so those would cancel out. So I have 4 divided by 3, and then 4, and then 12. Well, to figure out if this is truly correct and this is truly a geometric sequence, I can divide backwards. And so I could take 12 divided by 4, and that's going to give me 3. And if I take 4 and divide it by 4/3, well, that looks crazy because we are dividing a fraction, double-decker fraction. So that's the same thing as taking a 4 and multiplying its reciprocal. Those 4's cancel out, leaving 3. So I do have a common ratio of 3 in both cases, so I feel that my answer of k equals 4/3 is reasonable and correct. All right, let's look at one more semi-advanced example of geometric sequences. Again, we saw a similar example to this on our sequences video from a couple lessons back. A geometric sequence has a 6th term that's equal to 24, an 11th term that's equal to 768. Determine the general term of the sequence and hence find the 12th term. So I'm going to draw a picture. I have my first term, my second term, my third, fourth, fifth, and then finally my sixth term, which I know is 24, seventh term, eighth term, ninth term, 10th term, and then finally my 11th term, 768. Now our question is, how do you go from a sixth term to a seventh term? Well, you multiply by a common ratio. And then from the seventh term to the eighth term, again, I multiply by a common ratio. Eighth to ninth, multiply a common ratio, so on and so forth. Ninth to 10th, common ratio, and then 10th to the 11th term, I would multiply by one more common ratio. So how many ratios am I multiplying by? 1, 2, 3, 4, 5. So that tells me that I have 24 times r times r times r times r times r, or r to the fifth power, is equal to 768. Now, how do we solve this? Well, let's get our variable alone, just like we would in a freshman algebra class. What is 24 doing to those r's? It is multiplying, so we would divide both sides by 24. Those cancel out, and I get r to the fifth power is equal to 32. So I know some number times itself, times itself, times itself, times itself again, or 5 of those numbers all getting multiplied together equals 32. So one possible way to do this would be guess and check. Another possible way to do this would be taking a fifth root. Another possibility would be take this all to the power of the reciprocal of the exponent. So I was already taking it to a power of 5. Now if I take both sides to a power of 1/5, and you might say, well, that looks even more complicated than what we had before. But the thing is, I can put this in my TI graphing calculator and figure this out, because this 5 and this 1/5 are going to cancel out. And then r is equal to 32 to the 1/5 power. So in your calculator, you type 32 and then a caret symbol, which will actually make an exponent. Use some parentheses and do 1 divided by 5, and you will get an answer on the calculator of 2. So we can check that and would say, 2 times 2 is 4, times a third 2 would get us to 8, times a fourth 2 would get us to 16, and times another 2, that last 2, that fifth 2, would get us up to 32. So that does all make sense. Now, we're not done with the problem yet. We still have to actually write our general term and find the 12th term. So our nth term, or our general term, is equal to our first term times our common ratio to the power of n minus 1. Well, we're going to have u sub n is equal to our first term, which we don't know yet. So we have to sort of work backwards. And so previously we had multiplied r over and over and over. Now we're working backwards. So we're going to divide r once, twice, 3, 4, and 5 times to get us back to the first term. So I can take 24 and divide it by, again, we said 5 r's. 1, 2, 3, 4, 5. So r to the fifth power. But we already know what r is. It's 2. And we already know that 2 to the fifth power is 32. So we're taking 24 and dividing it by 32, which might look a little easier if I write it like a fraction. And 12 goes into both of those. Nope, sorry. 8 goes into both of those. 8 goes into 24 3 times, and 8 goes into 32. So we would have 3/4 as our first term. Now we can plug that in. So we have 3/4 here. We have our common ratio of 2. And then we have our power of n minus 1. We're looking for the 12th term, so we can do u sub 12 is equal to 3/4 times 2 to the 12 minus 1, or we can simplify that down to 11, and then we're going to plug that into our calculator. And we end up with 1,536. Now, because our common ratio was 2, we were doubling each time, and so we would expect to be getting bigger. And actually, if I go back to this problem, we arguably could have made this a little bit simpler, because we already knew the 11th term, and we would have only needed one more common ratio multiplying here in order to get to that 12th term. But now that we have our general term, which was what we were asked for, we could actually figure out any value at any time. And we figure that out right here after plugging in our first term and our common ratio. All right, that's it for today. Until